So imagine if we delayed teaching the alphabet to our children until they were 15 years of age. What effect would that have? Well, this is what I think. We'd suck at spelling, and we probably couldn't say or read the word Stone Age until we got to university, if at all. But there is a kind of alphabet that we do delay until they're 15 years old. In fact, in the case of the alphabet, we get in early because we realise this. So we get in at sort of like even before kindergarten, or even sometimes parents do it before birth. And it's for good reason, because they understand the benefits of an early start to the process of reading and writing. But in the case of the alphabet that I call the periodic table, that is delayed until we're 15. And if we just simplify the periodic table a little by closing the gaps and putting the rows together to make one long row, we can see that it is just a list, very much like the alphabet, except where the alphabet has 26 letters, the periodic table has 92 that show the 92 different kinds of atoms that make up our physical world. All of it. Even when we look into outer space, we see the same 92 kinds of atoms out there. And whereas in the case of the alphabet, we can build a word, we can do the same with the periodic table, except that we build a chemical word, or we call it a chemical formula. In the case of this particular chemical formula, HOH, it's got two H's in it, so scientists merge the H's and just put a little 2 down there to make it look simpler, if you think that's simpler. Now, in the case of the alphabet, all of the words, all of the letters and the words and the sentences together construct literature. In the same parallel way, all of the symbols, the letters of the periodic table and the formulas construct atomic theory. And the question I'm kind of asking today is, can primary school students understand atomic theory? Can they benefit from the same early start that we give with the alphabet? This question occurred to me when I had a walk in the park with my son, 7-year-old son, Tom, and he asked a riveting question. What's the world made of, Dad? You should never ask that question of a chemistry teacher. You might get the long answer. But the short answer, of course, is atoms, son. And the ensuing conversation, I realised that he could visualise the world microscopically as being made of these invisibly tiny particles that were bonding and unbonding and always moving. And that was the day that I realised that my son could understand atomic theory. But the question is whether other sons and daughters could also understand it. So intrigued, I went to his school, Ithaca Creek State School, and asked his deputy principal, Shani Tompkins, if I could visit his class. She agreed, even though this was going to be way outside the curriculum standards. And this is what happened.
Ian Stewart even delves into the structure of the atom, introducing protons, neutrons and electrons.
What are we going to do with lithium? Izzy?
We're gonna put 3 protons in the nucleus.
Exactly.
And then we're going to put, because the first shell can only hold 2 electrons, so we're going to put 1 electron on the second shell.
It's number 10 on the periodic table, is it?
Yeah.
So what's it got?
Classroom teacher Adrian Quinn says he can see his students understand the abstract concepts, which are so different to what's in their normal science lessons.
Well, from my perspective, I've been really impressed and surprised too. The kids have been really engaged, they've adapted to it well. Their recall has been quite good, so you can introduce a concept and a few weeks later something will come up and I'll relate it back to that concept, and you can see that the kids get that.
Oxygen, chlorine and neon.
Excellent. Well, it worked. It seems that his classmates could also understand atomic theory. And the thing, though, was I actually imagining it? Maybe there was some kind of confirmation bias in this, and I was having some wishful thinking. So what I really needed was some kind of hard evidence of learning taking place. I was very fortunate to meet Dr. Carol Heusler and Dr. Jenny Donovan from the University of Southern Queensland, who were science education researchers, and they agreed to test this bold claim. And we got a pilot study going with a school, a grade 4 class, and they did interviews with the students before a 10-lesson intervention that I gave. And this is their understanding before the 10 lessons. After the 10 lessons, dramatic increase in understanding to a kind of a high school level of understanding. Now, these were oral responses, and it's more research robust if they can get written responses. So they asked them if they could do drawings of their atoms and molecules. And here are some examples. In the case of Sebastian, he was able to draw an oxygen atom with its protons and electrons. We didn't cover neutrons in the class. And in the case of Lachlan, this is a really idiosyncratic diagram for an H2O molecule, but it's accurate. He's showing how covalent bonding can happen with the electrons of the oxygen and hydrogens overlapping to form bonds. Pretty advanced stuff. Another curious example was Marcia, who was actually in year 1, and she insisted on joining the class because her older brother was in it. And she, at the end of it, she was able to show that carbon dioxide had double bonds and it was linear. This is high school stuff. She was 6 years old. That's like 9 or 10 years in advance of what we expect. So the two big conclusions that Jenny and Carol came to were that, firstly, primary school kids understand atomic theory to a high school level. And perhaps more importantly, they discovered that they love it. They run to class, they take it home with them and talk about it incessantly at home to their brothers, and they try to teach their parents atomic theory. If there's a clash between atomic theory and swimming, they choose atomic theory. So it was really quite astonishing, the engagement that we got. But it's not really practical for a high school teacher to be teaching it around all these primary schools. What really is necessary is that primary school teachers be able to teach it. And Shani introduced me to a colleague of hers, Libby Jordan. And Libby was the principal of Eagleby State School, and she agreed to start this program in her school and have all of her teachers teach it. I would do the initial teaching, but they would then take over. Kelly Kemp was a very talented primary school teacher who led up the team, and this is one of her lessons with a grade 2 and 1 class.
Everyone say 2 hydrogen atoms. 2 hydrogen atoms. Now bring your hydrogen atoms together. Finish the left bond. Now everyone say hydrogen molecule. Hydrogen molecule. Everybody, in one hand, pick up an oxygen. Now we're going to take our atoms, and what are we going to do? We're going to bind your hydrogens to your oxygen. Water molecule. Say water molecule. Now,
What does it look like?
1 oxygen.
2.
Oh, fantastic.
Well, I hope you can see that they're really into it, and the standard is really high. The interesting thing is that this was a revision class. These kids learnt it a year earlier. Some of them were 4 years old when they were learning this material. So we obviously have an opportunity here to up our game as educators. We needed to now take it to the world because now we know that primary school students can understand it and primary school teachers can teach it. So Patna School in Bangkok is a British international school.
Definitely the children are ready. I was worried that the abstract ideas might kind of go over their head a little bit, but the way it's explained in a very simple way, using concrete resources and the microscopes has really helped them to understand. I think they are ready. So to actually see the atoms, do you remember the name of the microscope we would need?
Electron
microscope.
The initial session that we had on Monday was really interesting to watch because Ian started really slowly and he walked them very gently through. So by the end of the first 10 minutes he got to the point where he was explaining to them if they really wanted to see one atom in an apple, the apple would need to be the size of the Earth. And that blew their minds, so he had them hooked right from the start.
It's interesting that we introduce them to this concept in the sense that it's something they want to know.
Like just one atom. An element is only one type of atom in one whole object.
And in water, there's 2 atoms. 2 types.
What types of atoms are in water?
I know. The blue and
It's not called the blue thing. No, it's the one with the. You don't hear.
If I said water is H2O,
H2O.
what do you think it might be?
I forgot. No.
hydrogen.
Awesomely cute. And we've taken it further east to the Philippines. Here's an example which is a 1 hour lesson, or less than an hour, and you can see how much material that they cover. It's it's a 2,500 student school. Big ones over there.
There are 2 hydrogens in the molecule, aren't there?
Here.
And how many oxygens? We rip apart the oxygen and turn it into carbon dioxide, and then we breathe it out. I think this double stroke means.
Double bone.
Almost. You need another red one. You need 2 red ones.
Say something nice. Excellent.
You've blown it.
You win.
There we go. That's a good one. Congratulations. I think you win, actually.
So that lesson was less than an hour, and they started with an H2O molecule, then went to an O2 molecule, CO2, CH4, acetic acid, then amino acid, And then finally they built a protein molecule. And as Ruben Meerman says, the famous surfing scientist, these are the molecules that make their own bodies. So to understand and to be health literate, you really have to know atoms. So there are a number of reasons to teach atomic theory early, and one is that it'll be really, really good for society. Society will have more literate research scientists that can innovate outcomes, that can make us healthier and wealthier. And also research scientists are needed in order to solve the planet's problems. Like perhaps we can produce pocket-sized nuclear reactors or lab-grown meat and that kind of thing. So these are desperately needed solutions, and we can do this by having more literate students go through to our universities. But I think the biggest reason to do it is to make science interesting again. In primary schools, the lessons are capped at the senses, what the students what they can see and feel and observe is what they're limited to, like observing ice melting or bending plastic. But in order to see and observe atoms, you actually have to use your imagination. That's the sense that's required. And the imagination is without limit. So it means that we're giving students a much greater sense of space within the walls of the classroom. Because I think there's a sense of almost claustrophobia amongst primary school kids whereas if we can provide a kind of a mental pathway for them to see this vast microscopic world and build mental models of the world, we can set them free. And that's kind of what I sense about students when they're learning this, that they feel free. They're mentally free. It's like somebody who's in jail can be physically imprisoned, but they can be mentally free. So this is the basis of that. Now, what we're trying to do here is introduce this program to every classroom in the world, because we now have the evidence that students can learn it and that teachers can teach it. So if you know a primary school, if you know a principal or a student or a parent who are interested, or maybe you can suggest that they be interested in introducing atomic theory into their school, please do so, and we are absolutely prepared to help them do that. That's what we're now doing full time. That's our mission in life, is to make this happen. Thank you.